problem, I mean, I've seen this solution a while back, and now I am, basically going to code it myself after I understood the basic concept for this problem. So this problem is extremely popular. Actually, not sure why, but anyway, maybe it's because it's actually like quite a fun problem as well. So we see all the companies that have asked it in the last 6 months. Seems like Facebook loves to ask this question, Amazon. Anyway, so let's read the problem statement. Given an n by n 2D binary grid, which represents a map of ones, which are land, and zeros, which are water, return the number of islands, right? So basically it's, in essence, a traversal problem and a counting problem, okay? An island is surrounded by water and is formed by connecting adjacent lands horizontally or vertically. You may assume all 4 edges of the grid are all surrounded by water. And also here, like our input size is relatively small, so that is a sign that basically this problem can be solved with a brute force approach, meaning, for example, in an n squared time complexity. And also, well, here we have some examples. So here it says that in this example, the number of islands is 1. And according to this definition, like we can basically, kind of visually identify it quickly, right? So all of these ones are either connected vertically or horizontally, right? As we see, right? And then this one, which the expected output is 3 islands, we can also visually verify that. So for example, here we have one island, here we have 1 island, and here we have another island, and this is 3. Of course, that's because lands or ones can only be connected to each other either horizontally or vertically, not diagonally. But if they could be connected diagonally, like this example would be, in this case, the output will be 1, right? Because, for example, this one is connected diagonally to this one and to this one. So, but since that's not the case, that's why the output is 3. So the key concept to understand here is that this problem here can be basically think about or reasoned about like a graph, okay? And one hint here as well, it's basically because we have the word connecting, right? So there's basically connectivity between cells. So that's let's say like one logical way. But also in general, like any algorithm that runs, like for example in a 2D grid, there's always like the idea of adjacency. So for example in image processing, I forgot what that's called, but let's say image processing, I think it's called like 3x3 kernel filters. So for example here, there's always like some, like we have a neighborhood, for example, of pixels, and then some function is applied to, maybe this one is clear, a neighborhood of pixels, right? And then some function is applied to that neighborhood, and then we do that for every cell. And for example, we get this this new image, right, which is transformed. Maybe another clear example is this, right? So 3x3 filter, we multiply by some filter weights, we sum the result, and then we have like this new pixel values, for example, right? So that's an example. And since this is a 2D grid, like we can, let's say, process it like this in a similar idea. And at the same time, we can reason about a 2D grid being some sort of graph, right? So for example, if I will draw this idea really quickly, I'm just gonna create here like a quick board, these 3 columns, right? And then for example, in this case, since cells can only be connected horizontally or vertically, we know that this is one possible way of connecting, right? Or a possible way of connecting. Sorry, the drawing looks a little bit messy, but let me just put some points, right? Like here, so they're kind of seen as nodes, right? Like this here. Okay, cool. Okay, maybe it can even be drawn here in blue, these edges. But I think it's clear. The point I'm trying to make is clear here. Okay, cool. So that would be kind of like the connectivity, and this is just a graph, right? It's just a rectangular graph. Like a graph doesn't necessarily need to like be represented like this, right? That's like traditionally how we basically visualize graphs, right? Like in more in non-rectangular ways, but this is also a valid graph. And one thing to note is that this graph is also undirected, right? Because for example, this cell here can be connected to this cell, right? If we draw an edge like this with an arrow, and this cell here can also be connected to this cell here, right? So that's what it's called an undirected graph, because there's no like strict edge connectivity direction. But for example, a tree structure, on the other hand, is directed, right? Because in a tree structure, we have a node here, which let's say would be the root, and like if we just draw like a simple binary tree, we have its children, right? But in this case, only the parent node has access to its children, right? Its children do not have access to the parent node. So this edge doesn't exist, right, in a tree, right? That's why trees are considered to be, let's say, directed graphs, right, so to speak. Yeah. So basically, why I'm mentioning this is because in these problems, or let's say in any graph traversal, because like most, the majority of graphs are like undirected as well, or in graphs that are undirected, we need to keep track of the nodes we have basically visited to avoid infinite, like a never-ending loop or a never-ending traversal of a sequence of nodes, okay? So that's going to be very, very important. The next thing that we have to do is that we have to traverse all the cells, right? All the cells in the grid, traverse them, and for each cell, we are going to do a neighborhood check, right? Similar to like this logic here. For each cell, we're going to apply a filter that depends on the neighborhood, right, of each little cell. So basically in image processing, we apply a filter on each cell, right? So we have to traverse each cell and apply a filter. So we're going to apply the same concept here. So for each cell, we're going to check its neighborhood, okay? So let me, in terms of, okay, the explanation is very, very going quite a long way, but it doesn't matter. I mean, the solution is rather quick once we implement it. So let me just have, for example, this example here. I don't know if we can even, can it be like copy pasted somehow? No. but we have a text box. Okay, cool, right? So let me just draw this really quick. So we have for 1, 1, 1, 1, 0, 1, 1, 0, 1, 0. Then we have 1, 1, 0, 0, 0. And then we have all here, all water, right? So yeah, so as I said, like previously, the basic idea is so for each cell, we're gonna check our neighborhood. So for example, here, here, and here. And since we can only move horizontally or vertically, we will always have 4 possible movements for each cell, right? And that's how we're gonna basically do the traversal. So I'm gonna come back to this drawing in a bit. So let's start here the implementation. So one thing is that we're gonna do a nested for loop, of course. Then for row in length, so grid, and then we're gonna say and then we're gonna go through each column. Call okay, and then we are going to apply the DFS, right? So let's say pass, and then here we're gonna call our DFS, right? And we're gonna define that function here. So DFS. Also, I think one important thing to note here is that okay, we're gonna use a depth first search traversal and not a breadth first search traversal. So we're gonna use we're gonna use a DFS over a BFS, and it doesn't really matter. Like we can implement either, and the result will be the same. But the DFS just makes the implementation, yeah, just a little shorter in this case. But I mean, the main difference, I mean, these are 2 popular like hierarchical data structure traversal algorithms. So this can work on trees or in graphs. But the main difference is that this BFS uses a queue as a backing structure for the nodes to traverse, while DFS purely just uses a stack, right? And what this means is that the order of which nodes or edges, or however you want to call them in this case, the order in which they're traversed is different. But in this particular problem, it doesn't really matter. Okay, so we're gonna write this function out, and it's gonna take as input the grid, and we're gonna recycle this type, and it's gonna take into account a row index, right, and a column index. Okay, cool. And then one thing we also need is we need to take care of our edges, right? To not go out of bounds, right? So, like for example, to handle these cases, right? Like this, all the edges of the grid, any cell that's at the edge, we need to take care of, so we don't get an index out of bounds. So for that, we also will need to recycle this one here. So we say, we can say n rows, so get the number of rows, and then we can say here n columns to get the number of columns. Okay. Okay, and we are going to do this check. So right, so if row is smaller than 0, right, or row is larger than n rows, or call is smaller independent calls, right? We're doing the same logic for checking out of bounds for column and row index. And we also need to specify or if grid row call is occupied, right? Or it's occupied or is land, okay? And we're gonna do this check here. We will basically return, okay? So we will not process anything. So for example, like if we encounter a cell which is a water, like of course we have to ignore, so we cannot apply the depth first search to this cell, right? So this takes care of this. And also, for example, like in this case, in cells like this, like we could only move two ways, right? We can't move to the left or up because then we'll have an index out of bounds. So then we will return in those possible movements. And then after that, we will have to declare like an array that holds our possible moves, okay? So what possible moves do we have? We have, as I said previously, 3 possible moves, right? So we can move right plus right. We can move to the left, right? So sorry, this is kind of confusing. So we can move right. We can move left. We can move up, or we can move down, right? Right, left, up, or down, okay? So that's what we're gonna basically do. We're gonna have like a collection that stores these 4 possible movements, and then apply this movement recursively to every cell, right? So we're gonna say moves, we're gonna store those 4 possible moves. So here we're gonna say it's gonna move right. So here it's gonna move left, and then here it's gonna move up and down, okay? So those are the possible combinations. So right is gonna be 1, 0, and let me just clarify why it's 1, 0, because it's basically shifting, or it's gonna add 1 column to the right, So it's gonna be 1. So it's since a 2D grid has it's basically a coordinate system as well, like kind of like, for example, x, y. How, let's say, a right move will translate is like x plus 1, comma, y, right? Because we're not displacing ourselves in the rows, but only in the columns. And this is going to be applied for every left, up, or down move, yeah? 1, and then left is -1, and then we're not going to move it, of course, vertically, and then this is going to be up, and this is going to be down. Okay, so for I in the range moves, we're going to have our move here, and right, so, and then after this we're going to apply our recursive call. So we're going to pass the grid, we're going to pass the row, and we're going to pass the column. The row index and column index, okay? So here is where we're going to apply the offset. So plus zero, right? So here we're going to move right, and then here we're going to say plus and index 1, right? So we're not going to move in this case, for example. Oh, sorry, it's the opposite. So it's going to be 1 and 0, right? So we're going to move one column and stay put in the same row. So this is going to be applied for every cell, right? All the possible moves. Okay, so I think this is it. So we're gonna remove this, call this, and then I'm gonna say here, as in the grid, the row and the column. Cool. And then we need to also store the island count. So let's call it island count. And then we need to increment the island count, right? So for that, we need to return here 1. Basically, because at this point, we know that we have reached a piece of land, right? So whatever happens here, after this finished execution, we return 1 because we encountered like a piece of land, so we have to add +1 to it, right? And then here we should return 0 because basically we reached the condition that we cannot traverse, or it's a piece of water. Okay, so then here we have to store the result, and then here we say we add this by the result. Okay, cool. So as I think we're basically pretty much done with the implementation. So we're gonna just walk a little bit manually through this iteration here. So hopefully, let me just erase some of this stuff so it doesn't look that messy. Okay, and I'm gonna draw the one again. Okay. So the first cell we're going to encounter is this one here, right? So then this order also doesn't really matter. Like we could flip it around. That's what I'm guessing. We can try later with some unit tests, but I'm pretty sure it doesn't matter. So this is going to be the first movement, right? So we can move right. So this cell, of course, it can move right? Or it has a valid right neighbor, so to speak, right? So we will basically get to this point, so this condition is all false, so we keep here, and then we're going to iterate through the moves, right? And once we are here, we will add 1 to the row, and we will not move any row, but we will add 1 to the column, right? So then recursively the call will come here, and then this condition is still false, so we will move here. And now, of course, in this case, the row will be still 0 and the column will be 1, right? So then when we hit that second recursion call, we will be here, right? Because this is 0,1, right? We're still in the first row, and now we're in this column here. So that's gonna be applied, right? And so then this will be our other one, and then so forth, right? Until we reach this one. And that's also why it's called like depth first search, because we're going down this path until we can no longer continue, right? So we're basically moving to the right until we can no longer continue. In this case, for example, once we reach this guy, it can't move any more to the right? Because it encountered a piece of water. So it will hit this condition, right? And then it will return here, right? It will return here. So then we have to try to move to the left, right, which is the next step. But then to the left, we can't move because this has already been traversed. So then it will return again, right? It will return here. And then this for loop I is going to be 2 here, right? And it's going to try to move up. So this guy is going to try to move up, right? But then of course it will go out of bounds. So then it will return. And then the last option is to move downwards, right? Here. And that option is possible, right? So now this here will be 1, 3, right? Once we hit call recursively again, and then we're here, so row will be 1 and column will be 3, right? And then we repeat the process. For that cell, we're going to check, okay, we can move right, for example. So in this case, we can't move right as water, we can't move left, right? We can't move down because it's water, we can't move up because it's water, right? So we're at this path. So basically, since it can't move, we start like, you know, returning here, right? And once we are there, we're basically our call stack. If I draw our call stack, so our call stack has 1, 2, 3, 4, 5 frames, right? So this is our recursive stack, 3, 4, and 5, right? And then our start node, which is this one, is way at the beginning of the stack, right? Because that's how a stack works. And then this guy here, which is, let's call it for now the end one, is here, right? So then we're gonna start to pop all of these guys from the stack, right? Because, I mean, that's what happens when we start returning from the function. So then this is gonna be popped, right? So this is gonna be out of the stack. This one is gonna be also popped, right? This one is also gonna be popped. And then once we reach this one, right, we're here on this one. Remember that this one, when this function returns, I will be 1, right? So then this guy does have a possibility to move left, right? This guy here, but then it's occupied. And then this guy has the possibility to also move up, but of course it will go out of bounds. And this guy has also the possibility to move down, which is here, right? So then here where I is 3 and it can move down, so then this will continue to move down, right? And the process will repeat, right? So let's say we're here, and I'm just gonna, just for the sake of it, I'm gonna redraw the stack here. So then we will push this guy into the stack. This is gonna be the, you know, it's gonna be pushed into the stack, right? So then now this guy is here. This guy here is here. This guy here remains, right? Remains here. And then the start still is here, okay? And then the process repeats, right? Like this. Now this one here, for example, this one can move to the left, right? So let's just keep drawing. Just keep drawing the recursive call. This one can move left, for example. So we're gonna move here, right, which is this one, and then this one can move up, right? So this is the next call, right? So this is gonna now be our, let's say, our end node in this case, which is gonna be this one. But this end node cannot move anywhere because everything is occupied, right? So then basically we start popping away. So everything will start to return and return and return. So we're gonna, basically it's gonna be popped, oops, sorry, not here, obviously, it's gonna be popped, oh, sorry, here it's not yet popped at the moment. So then we're gonna return to the initial node, right? And what does that mean? That basically means that the initial node, remember, is, it returns here, and now I is 1, okay? So then we have these three possibilities to evaluate from the start node. Because if you guys remember, the end node, the start node only moved to the right, right? So then it will evaluate. But then of course all of these cells were previously visited, so it has nowhere basically to move. So then this will return, this will return, this will return, and then at the end this whole function will return here, right? And we know we have encountered a land, so it returns 1, and then here it will add the result to the island count, right? Because then finally this will be popped here after this returns, right? And that's basically how this works, right? After doing this walkthrough, is pretty clear and pretty detailed. So that's it. So this is basically a finished implementation, and I mean it's very simple implementation, very short. Conceptually, is very easy to grasp once you have the main idea. So let's try to run this problem. Well, one thing I do need to do before running it is return the island count. Okay, so let's run it. Okay, so it says island count int object is, oops, ha, of course, I forgot these guys here, range. Okay, so let's fix this. So range and range. Okay, now let's run it. Okay, what's up with this line 28? Line 2. Oh, again, ha! I forgot now. This time I forgot length. Take the length of this thing. Well, in fact, it's stupid, because we can always say it's 1, 2, 3, 4. But anyway, I mean, maybe possibly, you know, just for consistency's sake, it's better to keep it like this instead of hard coding any values. So okay, so let's run. Oh, okay, I see what I forgot. Yeah, maximum recursion depth, so Stack Overflow. So it's good that we hit that. Because that's what I was saying here at the beginning, right? So we basically hit a never-ending loop because we've never marked any nodes that we have traversed as visited. So that's why we hit a Stack Overflow. So to fix that, the easiest way to do this is to basically mark this current cell as visited. Oops. Okay, so we set it to 0. Okay, let's run it, and then, oh my god, more errors. We have an index out of range, and then this is because we are, of course, not saying subtracting -1 from here. Okay, and I think that should be it. So let's run it again, and perfect. Yeah. So that's really cool. So this initial test cases work. So like if we maybe try, for example, this test case here. For example, let's do all water. Okay, so let's run it. Perfect, it passed. Let's also just try. Let's try old land and see what happens. So old land should just return 1. That should be the expected output. So let's see if that's the case. Yes, perfect. It returns it. It returns 1. Cool. Now, for example, let's do something else, which let's only have one land, like one land, meaning one number 1. So let's just keep this one. And let's run it. Okay, that's cool. So I think the solution is ready. I cannot think about other edge conditions. So I'm gonna try to, hopefully it will pass all the test cases. So let's see. Oh yeah, that's cool. Generally, like these solutions, you know, we have to run it a couple of times. But anyway, let's just give you a more accurate result of the runtime. Okay, so it seems like it's for some reason not as such an optimal solution in terms of runtime. I'm interested to see other people's solution. Well, okay. I don't know, let's just see this C++ one. Why not? Oops. So this guy did a breadth first search, right? So it's using a queue. Yeah, I'm not really sure. Okay. Yeah, well, it's let's say it's the iterative version, of course, because it's breadth first search. So it's anyway. Well, cool. I mean, this one is in C++. Okay. Interesting. Here's a Java one. Also, they used a queue in this case, a BFS. I'm wondering if the BFS will be quicker. I'm not sure. Anyway, we can maybe try, or I can maybe try that solution as well another time. Okay, so this is it. I hope all my explanation was quite clear and these diagrams were quite clear.